Okay, so the goal of today is to find areas under curves, and then of course, the idea that we're going to learn with areas under curves, we're going to extend to how that also helps us find distances in certain scenarios. Okay, so what's cool about this section is that, we know how to find the areas of basic shapes such as circles, squares, triangles, and whatnot. But in this case, or in this section, we're going to learn how to find areas under curves, which the problem is curves could have any shapes and they're not necessarily circular. And since they don't have sides, we can't really break them up into anything to easily find it. So we'll use the ideas of calculus to help us find areas under curves. So basically, what we're saying here in this area problem is that if we are given a curve y equals to f of x, and whatever this curve is, obviously it needs to be continuous, because if it's not continuous, then we won't be able to kind of cover up or be able to enclose the region to find the area under the curve. Our goal is going to be, we will find the area of the region S that starts from x equals to a and goes to x equals to b. So in other words, if I were to kind of draw visually, what we're doing is, think of it this way. If I have a function that may look something like that from a to b, so if you notice, if we enclose this region from a to b, our goal is to find this region that we're calling S. So if you look at this, it kind of looks weird. You're like, well, how am I supposed to find this? The good news is we could find this area by using the ideas of calculus. So the comment that we can make here is that um, we know, so this is kind of like some things we know. Look, we could say finding areas of rectangles, triangles, and polygons is simple, right? Because we have a formula that allows us to find these, and we did this in geometry. But finding the area of a region with curved sides is difficult. Now, when I say that it's difficult in a sense where if we don't use calculus, it becomes fairly difficult. But we will take a certain approach to find these areas, which then will actually end up simplifying things for us. Okay, so like we're saying is, right now, or at least up to this point, we don't have the skills yet to find the area under this curve. But after this lesson, we will be able to kind of get an idea as to what the area under that curve is. So what we're going to do is we will use the ideas of rectangles to do this. So what we're saying is, to find the area under the curve, we're going to use the ideas of rectangles, and I'll go into detail as to what's going to happen here. Now, with that said, originally, a long time ago, people were trying to find areas under the curves of the sky by using triangles, but we noticed that, if we were to use rectangles, it becomes much easier to work with. Okay, so let's start off with an example where we will kind of, in this example, we'll illustrate how we will find the area under the curve. So let's look at an example. So example 1, we'll say estimate the area under the curve y equals to x squared from 0 to 1. Okay, so basically what we're saying is um, for this parabola, from x equals 0 to 1, I want to find the area under the curve of this. And the key word here is estimate. And we'll talk about how it's an estimate and how we can get a better idea as to, or how we can get a better approximation, or is it possible for us to get an exact approximation? So let me make some comments here. And then this note that I make here will actually kind of expand on this. So we will approach this problem with left endpoints, then right endpoints. Okay, so you'll see what I mean in a minute as far as left endpoints, right endpoints go. This just means, am I going to use the left endpoints of each one of my subintervals to find the height of the rectangle, or the right endpoints? So what we need to do is, if we're going to create rectangles, so for example, if we're doing this, if I were to draw this out, we want, in fact, we only care about the area under the curve from 0 to 1. So I want to find this area. So the first thing we need to do is to insert rectangles in here. What I need to do is I need to grab this subinterval from 0 to 1, and I need to divide it up. Okay, so what we'll do for now is, let's make a comment here. We will, let's just say, for example, let's divide the interval into 8 equal subintervals. Okay, so what we want to do is, I want to grab the interval from 0 to 1, and I want to break this up into 8 equal subintervals. So what does that mean? How would I divide this into 8 equal subintervals? Well, I need to find the length from 0 to 1, and I'll divide it into 8. Now, if you're wondering why am I choosing to divide this into 8 subintervals, it doesn't matter. Okay, in fact, we'll probably be able to make a comment about this as to what happens if I have less subintervals or if I have more subintervals. Okay, so let's do this. How far do I need to go for each subinterval? Well, to know the thickness of each subinterval, what do I need to do? I need to find this distance, which means I would say 1, which is my endpoint, minus 0, which is the start point, which that gives me the length of the subinterval, and I divide it into however many subintervals I want. So in this case, it's 8, which would be 8. So this ends up being 1/8. So what does that mean? Every time I break this up, each subinterval is going to have a length of 1/8. Now, one thing I want to point out is, see, when we're going to insert these rectangles in here, when I divide the subinterval up so I could insert my rectangles, we're always going to divide our subintervals evenly. Okay, now do we have to divide it evenly? Absolutely not. But we'll notice that for the sake of doing things, it just makes things easier for us. So if I'm dividing this up, here's what we're going to do. We're going to start with 0, and then if I'm breaking this up into 8 even subintervals, so let's divide this up. So we have 1, 2, 3, 4, 5, 6, 7. Let's divide one more up. So right there. So this is supposed to be 8 evenly spaced subintervals. So the first number here would be what? 1/8. Then the next one would be 2/8, which is 1/4. And then the next one would be 3/8. And then 4/8, which is 1/2. And then 5/8, 6/8, or 6/8 breaks down to 3/4, but you get what I'm doing. 7/8, and then 1. So what I just did is I broke this up into 8 evenly spaced subintervals. Now remember, when we're doing this, we don't have to make it evenly spaced, but it just makes things easier for us. So if we're using left endpoints, so let me kind of describe what this means. If we're using left endpoints, see what happens is each subinterval has a left endpoint and the right endpoint. So if I'm using left endpoints, what's going to happen is I'm going to use the left endpoint to go up to the curve to make my rectangle. So what happens is the will be what? This will be the left endpoint of each subinterval is used to create the height of the rectangle. Okay, so what that means is once I create the height, and by the way, the height of the rectangle is always going to start from where? The x-axis, and it's going to go up to the curve, because after all, why do I want to go up to the curve? Because my goal is to approximate the area under the curve. Okay, so let's actually draw this out and see how it looks. So if I'm using left endpoints, what do? I start from 7/8. So let's start from right and go to the left. So if this is my subinterval, that means I start from the left endpoint from the x-axis and I go all the way up to the curve. And once I hit the curve, then I go to the right to create my rectangle. Now notice how, what am I using? I'm using this rectangle to approximate this area under the curve. Now obviously, why is it an approximation? Because this rectangle doesn't capture all the area below the curve. In fact, what part does it miss? It misses this upper part. So that's why it's an estimate, okay? And if you're to guess, is it an overestimate or an underestimate? Well, obviously it has to be an underestimate because we're missing this part of it, okay? So then how would I create my next rectangle? I would go to the second subinterval, go to the left, go all the way up to the curve, and then once you hit the curve, move to the right. So there's my second rectangle. And once again, see these areas that I'm kind of shading, those areas have been, I missed those areas. The rectangle doesn't cover those areas. So this is going to be, the approximation of this area is going to be a little less. So the next rectangle is going to look like this. And if I continue doing this, I will have entered all of my rectangles. Now the last one basically is a rectangle that has no height, because if I start from the left endpoint, I'm already on the curve and I move to the left. So notice how when I inserted these 8 rectangles in here, when I find the area of each rectangle and I add them up, that'll give me an approximation of the area under the curve. It's not exact. You could see that it's an underestimate, but it gives me a good idea. Now, my question to you is, what do you think I would need to do to get a better approximation of area under the curve? And if you've already guessed it, we would have to insert more rectangles. So what are we saying here? The more rectangles we enter under the curve, the more our approximation becomes accurate to the exact area under the curve. So my next question to you is, how would I find the exact area under the curve? And so what do you notice? If I enter more and more rectangles under the curve, that means if I were to insert infinitely many rectangles under this curve, then I would get the exact area under the curve. So right now, we're just doing a finite number of rectangles. Eventually, in fact, in the next example, we'll get into probably inserting more than 8 or infinitely many. So coming back to this, what I need to do now is we need to find A1, A2, A3, A4, A5, A6, A7, A8. So I've labeled this as A1, A2, A3, A4, A5, A6, A7, A8. I need to find all of the areas one by one, and then we can add them up and get our area under the curve. And by the way, finding the areas of these rectangles is very, very easy, because now let's look at this. How would I find the area of the first rectangle? And see, here's another reason why I like to divide my interval into equal subintervals, is because what? All of these rectangles have the same length of base. All of their bases are 1/8. So to find the area of this rectangle, what do I need? I need the length of the base times the height. Now, the base we have, which is 1/8. How would I find the height? Well, look at the height of this rectangle. Where does the height of this first rectangle start? It starts from the x-axis, and it goes all the way up to the curve y equals x squared, and it ends on the curve. Now, if you remember, to find this distance, how would I find the height of this rectangle? Well, all I need to do is plug in this x value into the parabola, into x squared, and the y value will tell me what the height of this rectangle is. So if you remember, we've done similar things similar to this in the past. So that's how we're going to find the area of the first rectangle. So let's call the A1 would be what? It'll be the area of the, or the length of the base of the rectangle, which is 1/8, times the height of this rectangle, which, notice my sample point was left endpoints, so this height was drawn from 7/8 going up. So what does that mean? I'm going to plug in 7/8 into the parabola, which, when I do this and I simplify this, I should get 49 over 512. Okay, I hope this is okay. So now, how do we find a sub 2? Well, the second area, same thing goes on here. We find the length of the base, and when you find the length of the base, which, once again, what is it that we know? We know it's 1/8, so it'll be 1/8 times the height, and once again, since I'm using left endpoints, I would use 6/8. So you could plug in 6/8 here. And if you plug in 6/8, what do we get? We get 36 over 512. So moving on, a sub 3 would be the third rectangle, which means, once again, the length of the base is 1/8, and then I would use 5/8 to go up to the curve. So a sub 3 would be 1/8 times 5/8, and this should be squared, by the way, I forgot to put that, 5/8 squared, because remember, this is the height, which is found by plugging the 5/8 into the function, which is x squared. So that gives me 25 over 512. And then, so if I continue this process, which I don't need to refer back to the picture. I hope by now you know exactly what we're doing. What would the next rectangle have? A base of 1/8 times 4/8, which gives me 4/8 squared, which that's the height. So that gives us 16 over 512. And then the fifth rectangle would be 1/8 times 3/8 quantity squared, which is 9 over 512. And then a sub 6 would be 1/8 times 2/8 squared, which would be 4 over 512. And then the seventh rectangle would be 1/8 times 1/8 quantity squared, which would be 1 over 512. And the last one would be 1/8 times 0 squared, which, notice how the last rectangle has an area of 0, because obviously I started from the left endpoint and I'm already on the curve, so I just get kind of like a flat line there. So there is no rectangle there. So now what's my approximation going to be? The approximation will be, we'll say the total area is going to be approximately, if I grab all of these and I add them up, which I'm going to go ahead and just give that to you, it'll be about 140. I'm running out of ink, it looks like. 140. There we go. It's 140 over 512. Okay? Why is this not working? I'm going to use a pencil. Okay, so it's 140 over 512, which is basically our approximation. So if we want to kind of give this a decimal, as a decimal, it's like 0.27. Okay, so what is it? And by the way, we know that this is an underestimate because if you look at our picture, the areas are inside the curve. The rectangle misses parts of the inside of the curve. So now, before we move on to the next example, let's also use right endpoints. So what are right endpoints going to do? Right endpoints, all they're going to do is they are going to give us an over approximation. So hopefully you'll see why in a minute. So if I were to draw this out, so if we're using right endpoints, And by the way, this is also known as the sample points. So just so you're aware of this, in the future, when you're asked, hey, what are you using as your sample points? We're basically saying, hey, are you using right endpoints or are you using left endpoints to draw the height of your rectangle? And sometimes we'll even use midpoints. And we'll notice that midpoints actually end up being, as far as approximations go, they end up being the most accurate ones, okay? But we'll talk about that later. So let's use right endpoints. So if we're doing the same thing, if I'm drawing out this parabola from 0 to 1. So if that's 1, that's 0. And once again, what are we doing here? We're dividing this up into 8 even parts. Okay, so there we have it. So these values don't change. They end up being the same. So this is 7 eighths, 6 eighths, 5 eighths, 4 eighths, 3 eighths, 2 eighths, 1 eighth, and 0. So what am I doing now? I'm using right endpoints. So on this first subinterval, I start from the right side and I go up to the curve and I move to the right. Okay, so this rectangle is kind of harder to see. You'll see what's happening in a minute. Now this next subinterval, I move up to the curve, move to the right, and go down. Now what do you notice as far as our rectangles go? Our rectangles are going, they're covering the curve and then going outside of the curve. So when we use right endpoints, in this case, right endpoints end up being overestimates, okay? Now, one common mistake people make is they say, oh, well, then that means whenever we use right endpoints, they're always overestimates. Not necessarily. And we'll talk about what happens in a minute. But if I were to draw these rectangles out, now you could see that our approximations are going to be overestimates. So this is basically the same way. So if I were to label this as A1, A2, A3, A4, A5, A6, A7, and A8, to find these areas, how would I find A1? Area 1 would just be, once again, the length of the base, which is still 1/8. And then we'll multiply it by, now this time it's going to be what? The right endpoints to get to the height. So I'm going to plug the right x value of each subinterval to get into the function to get the height of the rectangle. So it'll be 1 squared. So this first one is 1/8. Okay? And then A2 would be what? It would be 1/8 times 7/8 squared. And then area 3 would be 1/8 times 6/8 squared. And then area 4 would be 1/8 times 5/8 squared. Area 5 would be 1/8 times 4/8 squared. Area 6 would be 1/8 times 3/8 squared. Area 7 would be 1/8 times 2/8 squared. And area 8 would be 1/8 times 1/8 squared. So if you're to add all these together, that would give me the total area approximation, which would be, in this case, 153 over 384. So I just went ahead and kind of did the math for you and gave you the total area. If you want to verify it, you could just kind of go through this, okay? But what that gives us is about 0.37109.3, so on. So what do I notice here? That this is an overestimate, the other one was an underestimate. So the actual area is going to be somewhere between these two. Now, my question to you is this: how do we get, so, and one other comment, we should probably write this is an overestimate. I mean, in the picture we saw it, right? But my question to you now is, how do we get a more accurate approximation? And then the answer to that is, well, we insert more rectangles. Okay, and so we could actually go further than that. We could say, in fact, um, if the number of rectangles approaches infinity, which means we're trying to insert infinitely many rectangles, then we will find the exact area under the curve. Okay, so now with that said, that's not easy because how could we insert infinitely many rectangles? Okay, because I mean, what is infinite? It's something that we can't really describe. So the good news is when we're actually entering these infinitely many rectangles, we are pretty much going to come up with a way, or we're going to come up with a formula that kind of helps us out here. So let's actually make that our next example. So for example 2, what we're going to do is we're going to say, what if we have infinitely many rectangles? So how's that going to change things, or how's that going to be different? So for example 2, let's write this out. Example 2, show that the sum of the areas of the upper approximating rectangles approaches 1/3. Okay, in example 1. So basically what we're saying is, in other words, here's what we want to show. And by the way, when we say upper approximating rectangles, that means those are the rectangles that go outside of the circle, which in this case it was the right endpoints. So here's what we want to show. We want to show that the limit as n goes to infinity, r sub n, see, r sub n means how many rectangles we're putting in. So as we put infinitely many rectangles inside the curve, and this capital R means that we're using right endpoints, this should equal to 1/3. Okay, so here's what we want to do. To be able to solve this, or to answer this question, we need to come up with a formula that gives us how we've entered n rectangles under the curve. So basically, I want to come up with a generic formula that says, look, here's the formula that will tell you the area when you've entered an n number of rectangles under the curve. So whether it's 2 or 5 or 10. And so why is that important? Because once we do that, then we could take the limit and send n to infinity, and that'll help us out. So here's what we need to do. To be able to do this, we're going to find the width and the height of the rectangles. And once we do that, then we're ready to go. So here's the problem. What I want to do is I want to divide. So if I had to, let's say, draw the interval out. Remember, our interval was going from where? From 0 to 1. And what do I want to do? I want to divide this up into how many subintervals? Remember, if we're generalizing it, I want to divide this into n equal subintervals. And if it's n equal subintervals, what does that mean? Well, remember for the first example, I said if I'm dividing this into eight subintervals, we said 1 minus 0 divided by 8. Well, if it's n equal subintervals, that would be 1 minus 0 divided by n, which means that gives us 1 over n. So what is this? This is the length of each subinterval. So if I were to come back over here, what would this be? This would be 1 over n, right? Because from here to here, I went to the right 1 over n. So from 0 plus 1 over n put me there. What would the next one be? It would be 2 over n. The next one would be 3 over n, 4 over n. And then what would happen? I would keep going until I hit what? N over n, which the last one is n over n, which that's how we get 1. So notice how the length of each one of my subintervals is 1 over n. So the good news is we already know, so here's what we could say. We could say, since these are evenly divided, and that's how we constructed this, that's good news for us. So we could say that the base of each rectangle is 1 over n. Okay, now what we need to do is we need to find the height of each rectangle. Now remember, the good news was each rectangle started from the x-axis, and then we went up to the curve to find the height of it. So now the next question is, well, what sample point am I using? Am I using left endpoints as my sample point or the right endpoints? And we said we are using right endpoints. So, and technically speaking, it doesn't matter if we use left or right endpoints, because if we're inserting infinitely many rectangles, whether you're using left endpoints or right endpoints, you're going to get the same answer. It's only when you have a finite number where your approximations will either be an overestimate or an underestimate. Okay, so coming back to this, what are we going to say? So the base of each rectangle is 1 over n. So how do I find the height? Let's look for a pattern here. So let's come back to this picture that I drew. So the first height is going to be what? In the first subinterval, I'm going to plug in the right endpoint into the function. And if you remember, the function was x squared. So what we could say is that, and each height for the upper rectangle is, so look at what happens. For the first subinterval, it'll be what? 1 over n squared. So that's going to be the height. And then for the second subinterval, remember I'm using right endpoints, so it'll be this one. It'll be 2 over n squared. And then for the third height, it'll be 3 over n squared. And we'll keep going until we hit the last subinterval. And on the last subinterval, what would it be? It will be just n over n, or just 1. So we can just to stay consistent, we would call it n over n squared. Okay, so the good news is now I've pretty much come up with a formula generalizing the area under the curve through n number of rectangles. So here's what's going to happen. So r of n, which by the way, this represents the sum of all the rectangles, areas of all the rectangles put together. So what do I know? The first rectangle is going to have what? Base of 1 over n, and the height, like we said, 1 over n squared. Plus, the second one is going to have an area of 1 over n times 2 over n squared. And as you could see, I'm going to keep adding these rectangles until I get to the last rectangle, which the last rectangle will be what? It'll have a base of 1 over n and the height of n over n squared. Okay? So let's actually start simplifying this. So here's the uncertain part. See, it's this dot, dot, dot. If I could somehow eliminate this, then things will become so much better for us. Now, with that said, let's start simplifying this. Now, the first thing I notice is instead of trying to multiply through, what I could say is, look, every single one of these have a 1 over n in common, and even a 1 over n squared in common. So what I'm going to do is I'm going to factor out a 1 over n and the 1 over n squared from this. So if I do that, if I factor out a 1 over n times, factor out another 1 over n squared, what am I left with? This is gone, so this just becomes a 1, plus what happens to this? This just becomes a, so that's 1 squared, this is a 2 squared, and then the next one would be a 3 squared, plus all the way until I get to n squared. Okay? Now, hopefully this looks familiar to you guys. Okay? So to simplify this real quick, this goes further as what? 1 over n times 1 over n squared is just 1 over n cubed. Now this turns in, this is basically 1 squared plus 2 squared plus 3 squared plus all the way to n squared. Now if you remember from an analysis, there's a bunch of sequences and series that we had formulas of, that we memorized and so on. If you remember, you guys remember these formulas where we said I equals 1 to n of I squared, which basically this is saying what? 1 squared plus 2 squared plus 3 squared all the way to n squared. If you remember these formulas, there's three main formulas that you were forced to memorize in analysis, and I'll give you those formulas later on. But this is that basically. And we knew that this sum we actually had a formula for, and that formula is actually n times n plus 1 times 2n plus 1 all over 6. So in other words, the good news is I can replace this with n times n plus 1 times 2n plus 1 all over 6. And if I do that, then this turns into 1 over n cubed times n plus 1 times 2n plus 1 all over 6, which then, if I were to simplify this, what do I get? Well, these n's cancel out, so that gives me n plus 1 times 2n plus 1 all over, this becomes a square, 6n squared. Okay, so if you look at this, this now, what is this? This is the formula for the sum of the first n rectangles inserted under the curve using right endpoints. Now, the question is, how could I find the exact area under the curve? Well, remember what we said. N is the number of rectangles you put under that curve. Now, if I want to get more accurate approximations, I'm going to increase n and make it larger and larger and larger. So in other words, how do I find the exact? Send n to infinity. So if I send the limit as n goes to infinity, that'll give me the exact area under the curve. So here's what we could say. So the limit as n goes to infinity of r sub n, that will be the limit as n goes to infinity of n plus 1 times 2n plus 1 over 6n squared. Now what we could do is we could kind of simplify this in a way where it's to our advantage. So this is limit as n goes to infinity of, what could I do? I could say this is 1/6 times n plus 1 over n times 2n plus 1 over n. So let's see what happened. This n squared I factored and I said n, and this is 1/6. So look at what happens here. As n goes to infinity, see, we could actually simplify this further, but look at what happens. As n goes to infinity, this is infinity over infinity. So if you use L'Hopital's, you get 1 over 1. You guys see that? I hope you do. And then this one is also infinity over infinity. So if you use L'Hopital's, you get 2 over 1. So what does this actually end up being? It ends up being 1/6 times 1 times 2. And what's 1/6 times 1 times 2? That's 1/3. So what are we basically saying? The area under the curve of y equals x squared from 0 to 1 is actually 1/3. Okay, now this might take a little bit of time to soak in. Okay, it just takes time, and of course we will actually do more with this to come. So we're almost done with the section, but let's actually kind of generalize what we just did. Okay, so let's generalize this whole concept. Okay, and the next definition is actually going to generalize what we just did. Hopefully, it'll make things a little better for us. So we're going to say that the area A of the region S that lies under the graph of a continuous function f is the limit of the sum of the areas of approximating rectangles. Okay, so what is this basically saying? It's basically when we say the limit, that's the limit that you take to infinity. So this is giving us the exact area. So in other words, here's what we're saying. A equals to the limit as n goes to infinity of r sub n, which these are the sum of all the rectangles. So, which in other words, this is defined as what? The limit as n goes to infinity of f of x sub 1 delta x, which remember, if I were to kind of ask you what this is, what is this? This is the height of the rectangle, this is the base of the rectangle, plus f of x sub 2 delta x plus dot 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 f of x sub n times delta x. Okay, so basically, what are we saying? This is the height of each rectangle. So the function is always used to find the height of the rectangle, and this is the base of each rectangle. And what is this? This is the formula for the sum of the first n rectangles added together. And how do I get exact area under the curve? It's because I'm sending n to infinity. So I'm inserting infinitely many rectangles under that curve. And when you insert infinitely many rectangles under the curve, you basically get your exact area. And by the way, since this is the base of the rectangle, how do we learn how to find delta x? Delta x is b minus a over n, right? Because this is the starting value, ending value. So this is the length of your interval, and I'm dividing it into n equal subintervals, okay? So just keep that in mind. So the width of our rectangle or the base of our rectangles are found like that. If you remember on the last example, what did I say? 1 minus 0 divided by n. But you could go from any two values. So that's why this is the more generic form of this. Okay? So before we talk about the distance problem, here's what we're going to say. One other thing I want to write in our notes. I already made a comment about this, but sample points, these are the points that we use to find and let's actually rewrite this. These are the points that we use in each subinterval to find the height of the rectangle. Okay, so what is it that so far we've used? What? Left endpoints, right endpoints, midpoints we'll also use, but you could use any sample points. You could even go a fourth of the way or 3/4 of the way. But we'll notice for the case that n goes to infinity, we either want to use left endpoints or right endpoints. So this could be left endpoints, right endpoints, etc. Okay, so it could be any one of them. All right, so now let's talk about the distance problem. Okay, so let's kind of summarize what is going on here. In summary, the distance traveled by an object is equivalent to the area under the curve of the speed function. Or, I mean, you guys know it as velocity, but I'm going to call it speed for now. But, you know, we also, I mean, we know that velocity and speed are tied together. So we could say velocity function. But there's more to come on this later on because there's something that I'm leaving out as of now that we'll talk about later on, okay? So we're talking about the area under the curve of the velocity function. So in other words, what we're saying is, look, if you give me the graph of a function that describes its velocity, the velocity of an object, and I ask you, hey, what's the distance that this object has traveled? If you find the area under the curve, you're practically telling me the distance that the object has traveled. Okay, now, with that said, believe it or not, you've been finding areas under the curve this whole time, in algebra 1, algebra 2, and pre-calculus and so on. Because look, what's the most basic uh, distance problem that you've worked with? You know from algebra 1 that if velocity is constant, then what did you find? Distance equals rate times time, right? This shouldn't be anything new to you. Now, look at what happens. But this is only true if your rate is constant. Now, how does the distance represent the area under the curve of your rate? Well, let's draw this out. Think of it this way. If this is time and this is the rate, right? Because that's r times t. Now, if you notice, if I want to find, let's say, the distance that a function has traveled in the first 5 seconds, what do you know? You go from 0 to 5, and your rate is always constant, which this is r. So what do I know? If I were to graph this function, since it's constant, it's just going to be a constant rate from 0 to 5. Now look, how would you find the distance that this object has traveled? You would say what? The rate times, if it's the first 5 seconds, 5. So you would say, for example, the distance that this guy has traveled is 5r. Well, look at this. The 5 is the base of our rectangle. R is the height. And what do you get when you take the time, which is in this case is 5, and you multiply it by r? Doesn't that give you the area of this rectangle? So notice how, since this is the velocity function, rate times time actually gives us the area under the curve. And in fact, this area is a rectangle because r is constant. So what we're basically saying is, look, if you have the velocity function, then you could find the distance that the function has traveled by finding the area under the curve. And how are you going to find the area under the curve? Well, for now, we're going to approximate it using rectangles, just like we did in example 1. So for example 3, which this will be our final example, we'll say find the distance traveled by the car given the following information. So I'm going to give you a table, say time velocity. So 0, 25, 5, 31, 10, 35, 15, 43, 20, 47, 25, 46, and 30, 41. Okay, so what do I notice here? We're given subintervals of 5 seconds, and then this gives you the velocity at each time frame. So now, if we're approximating this, we need to decide, hey, are we going to use right endpoints or left endpoints? And since we haven't been specified, we're going to say we'll use left endpoints to do this. So if I'm using left endpoints to approximate the distances traveled, I'm basically trying to find the area under the curve of this velocity function. So what do I know? The distance is the area. So let's start off with saying what? My first subinterval has a length of 5. So the base of the rectangle is 5. And the height, since I'm using left endpoints, between 0 and 5, 0 is the left endpoint. So the height will be 25. So that's the first rectangle. Plus, from 5 to 10, once again, the length of that interval is 5. And the left endpoint is going to give me a height of 31. Plus, this will be what? 5 times, then the left endpoint gives me 35. Plus, the next one is going from 15 to 20, and the left endpoint gives us a height of 43. And then plus 5 times between 20 and 25, I'm going to use 47. and finally plus 5 times 46. Okay, so once we do all this, we multiply this out and we add them up, we should get 1,135. Now, my question to you is this the exact distance traveled? And the answer should be, of course not. These are approximations, okay? And especially since we have a table here, I can't find the exact value. So this is an approximation of this guy, of the distance that this car has traveled. Now, the comment I want to make is that we could have even used right endpoints if we wanted. And another comment I want to make is, how would I get a better approximation of distance? And so think about that for a minute. Um, my question to you is, how would we have a better approximation of distance? So how would we have a better approximation of distance? Our approximation would be better if we broke this up into more subintervals, which means instead of going from 0 to 5, maybe I went from 0 to 2.5 and 2.5 to 5. So the more subintervals I have, the more accurate my approximation is. How do I get exact approximation? I would have to break this up infinitely many times. Okay, so the infinitely many times, we would have to come up with a way of kind of manipulating it where we could easily evaluate it. Okay, so that pretty much wraps up this section. Um, and so, like I said, we just kind of got started into finding areas under the curves. In this section, we're mainly going to be approximating areas under the curves. So we're going to insert a finite number of rectangles under the curve. In the later sections to come, we'll focus more on finding the exact area under the curve. So for example 2, the one that I did earlier, if you're a little confused with that, which I don't blame you for being confused, because it could get confusing if you don't follow it, and you'd probably have to look at it a little bit over and over again. Um, don't worry about that, because we're going to have more practice with it. Okay, so it will get better, I promise you. But as long as what we're doing here makes sense, we're inserting rectangles, and it's such like a cool idea, because we're finding these complicated looking shapes and curves, and we're inserting rectangles in them, and finding areas of rectangles are so simple, and just using rectangles, we're able to kind of get a good idea as to what the area under the curve is. Okay, so that basically takes care of this section. And there's more to come of this stuff. So like I said, you will get better as time goes on.